Science 10, Lesson C, B8, the last chemistry lesson. Woohoo! I wanted to say that I'm really proud of what you guys have been accomplishing. I know it's been a bit of a slog to get through all this chemistry stuff without kind of the face-to-face interaction, but I'm really proud of what you guys have been accomplishing, and I'm sure you guys have done your pick sheets already, but some of you might be interested in pursuing chemistry eventually as Chem 20 and Chem 30 through ADLC, CBE Online, or even heading over to Central Memorial for a class. You guys are doing awesome, so I'm really proud of what you guys have accomplished. So next we'll head into biology and we'll kind of pick and choose what we can accomplish there. We definitely won't have time for that last unit of Science 10, but c'est la vie. That's what happens when you're in a global pandemic. Um, so mole conversions. This is that same mole that we were talking about yesterday. So again, or last day, or whatever schedule of events life is right now. Last day we talked about the mole as kind of a word used to represent a number, and that number was 6.022 times 10 to the power of 23 particles of a substance. So now that we know what a mole is, so again, that Avogadro's number, 6.022 times 10 to the power of 23, and how to calculate the molar mass of a substance, we need to look at what that means in a chemical reaction and how we can use it. So consider the following reaction. So this reaction is already balanced. It has states. The chemical formulas are correct, right? So something like PbCl2. So we know chlorine forms a 1 minus. So if we have two 1 minuses, we know that that needs to be lead 2 plus in order to balance out. That's where that all comes from. So again, these are all skills that have come up in all of chemistry so far. But in this case, we're given the reaction. So it says, if we are to interpret this equation, we would say that two particles of sodium chloride, NaCl, react with one particle of lead 2 nitrate. I think lead is multivalent, to produce two particles of sodium nitrate and one particle of lead 2 chloride. So realistically speaking though, can we precisely measure out two particles of salt? Again, salt is NaCl. This is table salt. There's lots of other salts. This is table salt, the stuff we eat. So not likely. Two particles of sodium chloride are so small. You wouldn't be able to precisely measure out two particles of salt. But in a chemistry lab, you need to be able to measure out precise amounts of these chemicals. So we have to be able to quantify the amounts of these chemicals in the lab. So we need more quantifiable. So again, when we're talking about quantifiable, again, that's quantity. So that's talking about a number. Qualitative analysis or qualitative measurements, we're talking about the quality of it. So things that you can observe, you don't have to measure. So when we're talking about quantifiable things, that's measurable units rather than simply individual particles. So if we look at that reaction again, this is that same reaction that we had above. Our balancing is important here. So if you can't write a balanced equation, these questions will be tough. So 2 sodium chloride plus 1 lead nitrate, lead 2 nitrate, produces 2 sodium nitrate plus 1 lead 2 chloride. So again, what it's kind of saying is two particles of sodium chloride react with one particle of lead 2 nitrate to produce two particles of sodium nitrate and one particle of lead 2 chloride. But again, this is small. So what a better ratio might be is if instead of a particle, we take 6.022 times 10 to the power of 23 particles. So 2 times that number, 1 times that number, 2 times that number, 1 times that number, which actually represents out our ratio, our molar ratio is what we'll call that. That 2 moles of sodium chlorides, that's 2 times Avogadro's number, react with 1 mole of lead-2 nitrate, so that's 1 times Avogadro's number, to produce 2 moles of sodium nitrate and 1 mole of lead-2 chloride. So this is our molar ratio, we'll call it. So for the above reaction then, we can now say 2 mole of sodium chloride reacts with 1 mole of lead nitrate to produce 2 moles of sodium nitrate and 1 mole of lead chloride. We can now precisely measure these quantities in the lab. So these are bigger masses that are easier to measure. So we can also use the mole to describe a compound. We've already kind of talked about some of this stuff. So in 1 mole of aluminum carbonate, am I right in that one? Yes, aluminum carbonate, so Al2CO3, there is 2 mole of aluminum and 3 mole, again this 3 applies to everything in the brackets, so 3 moles of carbonate, which from there we could then kind of split that into 3 moles of carbon and 9 moles of oxygen. So hopefully that makes sense, that within 1 mole of this, there are actually 2 moles of aluminum and 3 moles of carbonate. And again, within that carbonate, if we have 3 of those CO3s, there's 3 moles of carbon and 9 moles of oxygen. So the next one says in 3 moles of calcium carbonate, or sorry, calcium chloride, so that's saying 3 CaCl2, there are 3 moles of calcium, and 3 times 2, in total, 6 moles of chlorine. Sorry, I had to pause for a second. Hope I was done that question. Then there's kind of a last question. It says, what if you only had 0.5 moles of calcium chloride? So, you know, we don't balance like this, so 0.5 CaCl2. What you would actually have is 0.5 moles of calcium, and if we take 0.5 and multiply it by 2, 1 mole of chlorine. And yes, you can have half a mole of something, just like you can have half a dozen eggs. Half a dozen eggs is 6 eggs, right? Half of a dozen. Half of a mole is half of 6.022 times 10 to the power of 23 molecules or particles or formula units, depending on what we're talking about. So let's look at this. So conversion factors. This is, we did this in physics. We did conversion factor stuff. So when we get to the questions, I'll do both by conversion factors, but I'll also give you the formula for relating our number of moles to the mass and to the molar mass. But we'll talk about conversion factors for a little bit first. So in chemical equations, we talk about chemicals in moles. We've already said that. So we have an equation here. So hydrogen gas plus oxygen gas producing water vapor. So another way that we could say that is 2 moles of hydrogen reacts with 1 mole of oxygen to produce 2 moles of water. And you can see that those numbers come from the balancing of the equation. Again, things to keep in mind, hydrogen and oxygen are both found diatomically, so if you're given your word equation, you need to write that out. So again, we don't have a scale in the lab where you pour something on and it tells you that's 2 moles of something. We can't measure moles because again, moles are a number of particles. So we measure things in grams. That's what the scale is. So we measure the mass of something, not the number of something. Again, a mole represents a number of particles. So we need to be able to convert, and again, we're converting mass to grams. So we need to use conversion factors to help do that. So just to kind of refresh, this is just a little notes on conversion factors, but we've done it before. So conversion factor is a relationship between two units that are measuring the same type of thing. So in physics, we did a lot of conversions of meters to kilometers or kilometers to meters. And we did a lot of conversions of time in seconds to time in hours, those sorts of things. So we use conversion factors typically for that. So we quite often set them up as a fraction here. So 1,000 meters over 1 kilometer. These represent the same amount, right? 1 kilometer is the same thing as 1,000 meters. Or we can write it the other way. 1 kilometer is the same as 1,000 meters. Having a fraction with the two things that represent the same amount in the end, 1,000 meters and a kilometer are the same amount. Having a fraction like that represents as 1, since it's the same thing. So 2 kilograms, just to do an example to kind of represent this, 2 kilograms contains how many grams? So 2 kilograms. So when we do conversion factor stuff, we multiply by our conversion factor. So back into physics, we know that we had kilograms on the top, so we want kilograms on the bottom. And which is bigger? I always asked you in physics, which is bigger, a gram or a kilogram? So a kilogram is bigger. So how many grams fit inside of it? Remember the word kilo, just like kilometer. Kilo means 1,000. So 1 kilogram is the same thing as 1,000 grams. So we can set up our conversion factor like that. Again, we want to be able to cancel out units. So kilograms on top cancels with kilograms on the bottom. Maybe I'll just keep my screen like this. Hopefully you can still see okay. So in our calculator, we would punch in 2 times 1,000 divided by 1 in theory. And what we would be left with is 2,000 grams. 750 grams contains how many kilograms? So always starting out with the given information. So this was our given information. That's why I wrote it first. So my given information is 750 grams. My conversion factor is the same thing as up here. I'm using the same conversion factor, but now I need to think about where I want each of these substances. So I have grams on top right now, so I want grams on the bottom. So you can see that I've flipped over my conversion factor here from the original. So here I was starting with kilograms, here I'm starting with grams. So in your calculator, grams on top cancels with grams on the bottom. In your calculator, you're going to put in 750 multiplied by 1 divided by 1,000, or just 750 divided by 1,000 gets you 0.75 kilograms. So not a full kilogram, 750 is less than 1,000, so it's a fraction of a kilogram, 0.75 kilograms. So hopefully that's a bit of a review on conversion factors, how we use them. So mole conversion factors, oh sorry, I think I missed something there. Maybe I didn't have it on my slide. I don't know if you have this on your sheet, but there's a little bit at the bottom. It says, although we usually express molar mass. Oh, sorry. No, it's on this page. Mine's set up differently. So mole conversion factors. So the word amount, so if you see amount with the symbol N refers to the number of moles of a substance present in any given mass. The word mass with the lowercase m refers to the mass in grams of a substance present in a given number of moles per amount. And molar mass, you see, is with a capital M. So you got to be really specific. Some of you guys that are driving me nutso with your nomenclature having letters that look like capitals at the beginning need to be very specific here because we have a lowercase m and an uppercase m in this. So the uppercase m is our molar mass in grams per mole. That's what we calculated out yesterday. The lowercase m is mass in grams, and n is the number of moles of a substance present in any mass. So although we usually express molar mass as grams per mole, it can be stated as, sorry, I have a crying child right now. Okay, my husband's dealing with it. Although we usually express molar mass as grams per mole, it can also be stated as moles per gram. Just like there are 100 pennies in $1, $1 contains 100 pennies. So you can kind of flip it around. So we have two conversion factors we will use in mole calculations. So the first one here, molar mass, so it relates moles to grams or grams to moles, depending on which way you're going. So, oh, is this a blank on yours? It might be, or it might not. So the molar mass of carbon, so from your periodic table, the molar mass of carbon is 12.01 grams per mole. Again, that's the average mass of all of the isotopes of carbon. So the two ways that we can write this is there are 12.01 grams per mole, or 1 mole is equal to, or is the same as 12.01 grams. This is, again, for carbon. That ratio is different for every substance. So if we look at beryllium, this number would be 9.01, 9.01. So we can use these conversion factors to convert the following. So we can use this conversion factor to convert from moles to grams, or we can use this conversion factor to convert from grams to mole. This is going to hopefully make a little bit more sense once we actually look at the types of problems that you'll see. So other conversion factors that we will use in mole calculations is related to Avogadro's number. So this is relating the number of moles to the number of particles within it. So this you'll see a little bit less often, but it can still come up. So 1 mole of any substance contains 6.022 times 10 to the power of 23 molecules, atoms. You could also see particles, formula units. Instead of molecules or atoms. So that's just saying an individual sodium chloride or whatever I had before, an individual carbon molecule, particle, atom. Molecules and formula units are a little bit different, so that should be talking about molecular and ionic compounds respectively. So our conversion factors are 1 mole is equal to 6.022 times 10 to the power of 23 molecules, or 6.022 times 10 to the power of 23 molecules is the same as 1 mole. So we can use these conversion factors to convert from moles. Yes. Sorry, these ones are kind of backwards. We can use this one to convert from moles to molecules, and we can use this one to convert from molecules to moles. So when you are converting between units, you always want to start with your given, and then you want to use your conversion factor to convert them from one to the next. So multiply by the unit you want, divide by the unit you have. This is like, again, we did this type of thing in physics, so even though that's kind of wordy, it should make sense what I'm talking about there. So this next question, I'm first going to do it by conversion factors, and then I'm going to give you the formula that you can use, because you'll probably, actually, if you take Science 20 or Chemistry 20, you'll probably use the formula more than conversion factors, but you'll see that it's doing exactly the same thing. So what is the mass of 7.50 moles of water? So we're given, if I go back to the old physics thing, so I'm given, so, sorry, number of moles, again, N equals number of moles, 7.50 moles. And we're looking for the mass in grams. My conversion factor is going to be my molar mass of H2O. So to figure out my molar mass of H2O, so 2 hydrogens, 1 oxygen, so 2.02 grams per mole. 1 oxygen is 16.00 grams per mole. So my molar mass of water is 18.02 grams per mole. So my conversion factor is 18.02 grams per mole. Or again, you can write it the other way. 1 mole is 18.02 grams. So using my conversion factor, or by conversion factor, so when we do conversion factors, we start with what we're given. So I'm given information of 7.50 moles, and we want to multiply by our conversion factor. So since I have mole here on the top, I want mole on the bottom, and I want grams on the top. So 1 mole is the same as 18.02 grams. And so in the calculus, sorry, I'll represent this. That mole on top cancels with mole on the bottom. So in your calculator, you would punch in 7.50 times 18.02 divided by 1 if you felt so inclined. And you would get 135.15 grams. So again, your units that are left over are grams. And again, it's asking us our mass. So we would get our answer in grams. So the mass of 7.50 moles of water is 135.15 grams. So what I'm going to do, sorry, I just flipped up a little bit, is I'm going to also give you the formula. Actually, you might, if you have a little bit of room here. So the formula that you might use instead of conversion factors, N equals, so N again representing number of moles, equals lowercase m over uppercase M. And so again, these 3 variables are right here. N, lowercase m, uppercase M. So this formula is in your data booklet. Let me just figure out where exactly it is. Hopefully I gave you that page. I did. It's underneath your solubility chart. So it's on page 10 in your data booklet. You'll see below it says stoichiometry and solution formulas. And you'll see there it says N equals lowercase m divided by uppercase M. And if you look kind of over to the right there, it gives you what N, lowercase m, and capital M actually represent. So this is the formula if you don't do it by conversion factors. Again, it's the same thing. Some people just recognize formulas a little bit better. So you're only given it as calculating number of moles equals mass divided by molar mass. If you rearranged it, if we needed to calculate out the mass of a substance, again, if you wanted to isolate this variable, I'm going to just draw a little If I wanted to isolate that variable, I know I need to multiply both sides by uppercase M. So mass is equal to number of moles multiplied by molar mass. So this is another formula that you might see or you might use. It's just a rearranged form of this. Very rarely would you be searching for the molar mass of a substance. I can't imagine a question where you'd say, what is the molar mass of this if you have number of moles and mass, but I guess it could happen. So our rearranged form of that one would be mass divided by number of moles. And so again, this one you won't really see. This has probably taken some of you guys back to physics, whether you like it or not. So I'm going to go back to that question I just did. So this was by conversion factor, but now I want to do it by formula. And honestly, most of the time I probably use the formula over conversion factor, but like I can't stress this enough, you're doing the same thing. So by formula. Again, I'm going to use basically what I had written up top. So my givens, N equals 7.50 mole. I'm looking for mass, and I know the molar mass of water. I would have had to calculate it out, but the molar mass of water was 18.02 grams per mole. I calculated that out up above here, and I just called it my conversion factor. So by formula, the formula is number of moles equals mass divided by molar mass. But I'm looking for, again, I'm looking for my mass. So mass equals number of moles multiplied by molar mass. So again, what I've done there, if it will let me escape, is I've rearranged this to solve for that by multiplying both sides by uppercase M. And so that's how I got to that formula. Am I still yellow? Oh, gross. It's so hard to see. And so mass equals number of moles multiplied by my molar mass, 18.02 grams per mole. That's 135.15 grams, which, lo and behold, is the same as we had here. And you can see that it makes sense. 7.5 times 18.02 is the same as 7.5 times 18.02. So you can do this by formula if it helps to not have to try to think of your molar mass as a conversion factor, or you can, you can do it either of these two methods. So on to the next one. So the mass of an iron bar is 16.8 grams. So given mass 16.8 grams, what amount in moles? So again, moles is my question mark, which is N, of iron is in this sample. So we know, I'm going to do this one by formula first. So by formula, and then we'll do it as a conversion factor. So I'm talking about iron here. That's something that you need to recognize. So our molar mass of iron, you need to look that up in your periodic table. It is 55.85 grams per mole. So our formula equals N equals mass divided by molar mass. Again, we're looking for N in this case, so we don't need to rearrange anything, but now we need to substitute in our given values. So 16.8 grams divided by 55.85 grams per mole gets us, oops, 0.301 moles of iron. So now if I do it by conversion factor, just to go back to that if you're more comfortable with that. So again, mass 16.8 grams. Our conversion factor is 55.85 grams per mole, or we can write it per 1 mole, or we can write it as 1 mole per 55.85 grams. So setting it up when we're talking about conversion factor stuff. Oops, I can't put that on there. Conversion factor, you always start with what you have. So 16.8 grams. Setting up our conversion factor, we know we have grams on the top here, so we want grams on the bottom in our conversion factor. So 1 mole is 55.85 grams. And so in your calculator, you'd be punching in 16.8 multiplied by 1 divided by 55.85, which is 0.301 moles. Yay! So again, you don't need to do this both methods. Whichever one works, just make sure you're showing me kind of your process. So if you're not getting the right answer, I can tell what you have done wrong. So if you're doing it by formula, write out your formula, show me your substitution so I can figure those types of things out. So question 3 here for the practice problems, how many formula units, particles, whatever you want to call it, atoms, a little bit weird to call it that way, are there in 1.34 moles of potassium sulfide. So this one we actually kind of just need to use conversion factors because this is not converting mass to moles or moles to mass. This is saying if I have 1.34 moles, how many particles is that? So in this case, we need to use Avogadro's number. And so what we're going to do, again, starting with what you're given information about. So 1.34 moles of potassium sulfide multiplied by, so our conversion factor. So Avogadro's number is our conversion factor. So we know that is saying 6.022 times 10 to the power of 23 particles is equal to 1 mole. So since I have mole on top, I want mole on the bottom. So we know that 1 mole is 6.022 times 10 to the power of 23 particles. So here's hoping you can put this into your calculator properly. What we would end up getting is 8.07 times 10 to the power of 23. Oh, I guess I've switched from formula units to particles. I'll probably answer it in formula units just in case. So 8.07 times 10 to the power of 23. Again, moles have canceled, so we're left with particles, which I'm going to just switch back to formula units because I don't know why I ditched that suddenly. So formula units in 1.34 moles of potassium sulfide. So in this case, we didn't actually we didn't have to worry about this, like what it actually is, because again, it's just telling us 1.34 moles of something. How many formula units is it made up of? A few more, guys, we're almost done. Oh, this is a long one. So how many molecules, again, this is the same type of question. So it's asking how many molecules of propane given the number of moles. So this one, again, we need to use Avogadro's number in order to do the conversion. So convert with Avogadro's number. So start with what you know, 0.52 moles. Multiplying by our conversion factor, again, we want mole on the top and molecules on the, sorry, mole on the bottom, molecules on the top. So 1 mole is equal to 6.022 times 10 to the power of 23. So that will get me 3.13. 3.13 times 10 to the power of 23 molecules. So that's saying in just over half a mole, there are 3.13 times 10 to the power of 23 super tiny little individual propane units within it. So we don't need to calculate out the molar mass of propane. All right, last one. Consider the compound iron 3 sulfite. I don't think we need to, but just to write out the chemical formula, iron 3, so we know that's iron with a 3 positive charge. Sulfite is SO3 with a 2 minus, so that would be Fe2SO3, 3. So if we need to calculate out the molar mass, we'll use this. But let's look. It says how many moles of iron would be in 1 mole of iron 3 sulfide. Okay, we did actually need the formula in this case. So how many moles of iron would be in 1 mole of iron 2 sulfate? So if we have 1 of this, I'm just writing the 1 there for now, 1 of this, we would actually have 2 moles of iron based on this 2 required for balancing. So 2 moles of iron. How many moles of oxygen would be in 1 mole of iron 3 sulfite? So again, we have SO3 3 times, so there are 9 moles of oxygen. How many moles of iron would be in 2.5 moles of iron 2 sulfate? So now, instead of a 1 here, now we have 2.5. I know we don't balance with a 2.5, but it's saying if I had 2.5 moles of that, so 2.5 multiplied by 2 is 5 moles of iron. And now the last question, hopefully you're not doing this too, is saying how many moles of iron would be in 0.25 moles of iron 2 sulfate. So 2 times 0.25, sorry I've switched the order from that last one, is 0.5 moles of iron. So you could see that type of question as well. Again, oh sorry, I'll let you finish copying if you're doing that. Again, you'll see kind of a variety of questions. I was smart enough to not do all of the worksheet in this, but you'll see in the assignment, if I can get to it. So some of them, I would go through, some of you guys were absolutely incredible in chemistry that you would sit and you would highlight words. So you'd say mass, moles, you would write out your given. How many moles would be in this mass? How many moles of each type of atom? So you need to write out the chemical formula. what molar amount? So this is saying how many moles. Sorry, that's kind of confusing. How many moles? So that's your N value. What number of moles would contain 2.86? So this is an Avogadro's number question, and so on. So those are your last couple of questions. So it just goes up to 8 there, I believe. So do that worksheet, and then that's the last worksheet for marks for chemistry. I'll get you guys a review set of questions for early next week. And then you guys will have your Chem B test, and then we're done with chemistry. So you know how to reach me if you need any help with any of this stuff. We will chat with you later.